This video is about discrete random variables in probability, and so let's have a look at what we've got here. This is the sample space. If we're using Venn diagrams, we'd call it the universal set, but this is the sample space for tossing a coin 3 times. Let's focus on the number of heads that show upwards. Okay, let that be the focus of our little inquiry here, the number of heads. And that will become the discrete variable, or the discrete random variable would be the number of heads. So discrete random variable is usually denoted by capital X. So for this one, if we create a little table out of this, and I've got a row there, and I split these different outcomes into columns. The X values can be written there. X, well, we've got HHH, so that's 3 heads. So X is 3, 2, just 2 heads there, 2, 1, 1, 1, 0. So we have some sort of distribution there. So the values that X can have, you can see there, I've grouped them. X can be 0, 1, 2, or 3. So X is our random variable. Okay, so X here is our random variable, but it's also discrete because it takes on discrete countable values. So in a previous video, I would have gone over discrete and continuous variables or data. Okay, we're talking about random ones in this video. So it's the random discrete variable. Its possible values are 0, 1, 2, and 3 in this case. Remember, discrete variables have specific values and they can't have anything between those particular specific values. Usually it's countable things. That's usually the way of telling, as opposed to measurable, so countable. Now back here we've got 8 possible outcomes, 1, 2, 3, 4, 5, 6, 7, 8 ways of this happening. That's the entire sample space, 8 outcomes. And so for our probabilities, when the random discrete variable is equal to 3, that's 1 out of 8. These are all equally likely too. We know that from our previous work on probability. So that one is 1/8. For 2, we've got 3 ways that can happen. So when the random discrete variable equals 2, we have 3/8. You can see there in purple. Same with when the random discrete variable is 1, we've got 3/8 there. And for 0, it's 1/8. And if we add those fractions together, we get 8/8, which makes sense because that's the probability of everything in the sample space taken care of there. We could draw a table to summarize that information as such. So we can see that a random variable is a function that assigns a number to each outcome in the sample space. So that number is a probability. The random variable can be discrete or continuous, but in this video we're focusing only on discrete. A discrete random variable is one which can take the place of a countable number of distinct values. Okay, like we said there. And that links to what you should already know about statistics and probability. Writing it in function notation, so the probability distribution written as a function, so there's your function notation. Instead of f of x, we've got p of x, is the probability as x takes on the various discrete random variable values. There are 2 results around that the value of p of x, unsurprisingly, should be between 0 and 1 inclusive, so you know that from your work on probabilities. And secondly, that sum of all the values in p of x equals 1. So all the values in p of x, sum them together, you've got 1. I'm going to do 3 examples now and consider the probability distribution given there and use the table to find So we've got the variable in the first row and the associated probabilities in the second row. And the first one says exactly 3. So when x is exactly 3, what's the probability? And the answer is 0.1. X is less than 3. Now what we have to do is look carefully at less than. Less than doesn't include 3, so because it's discrete, the next spot would be from 2 down, and the lower end of this probability is when x is 1. So we would have to say it's that and that. So we add the probabilities together, and we've got 0.2 plus 0.3, which is 0.5. The reason why that is because it's the probability of x equals 2 plus the probability of x equals 1 added together. Part C, the probability that x is greater than or equal to 4. Now that's inclusive, greater than or equal to, so there we are looking, and that'll be probability that x equals 4 plus probability that x equals 5 plus probability x equals 6, which would be 0.2 plus 0.15 plus 0.05, which is 0.4. Next one here, the probability 3 is less than or equal to x, which is less than or equal to 5. So that includes 3 and 5 and everything in between. So that would be there. So we have in our sum, without writing the notation down just to save some time, you probably should write the notation down for good justification. We've got these here, and we have 0.45. Not equal to 5. So that's 1 minus, we can use the complement, 1 minus x equals 5. It's the quickest way of doing it, using the complement, and that would be 1 minus 0.15, which is 0.85. So we've got another example here. We'll go through this one quickly. We've got distribution, random variable x. It's discrete, and given the, let's look at these various questions here. Probability that x is greater than 4. That's very much like what we did in the previous ones. We just add 5 and 6 together, and we get 0.36. This one here, like one of the previous ones, but it's not inclusive. Okay, that does not include 2 and 5, so it's only 3 and 4 added together. We get associated probability of 0.24. This one here needs a bit more focus. So the probability that x is greater than or equal to 5, given that it's greater than or equal to 3. So that's a conditional, you might remember you worked from previous units, conditional probability. You may need to revise that. Now, conditional probability, the probability of A given B is the probability of the intersection of A and B over the probability of B. Okay, need to recall that, and then once you know that, and you know that intersection means and, we look at, there's your and of the two parameters on the top, and that would be a parameter A and parameter B, and you see it just follows. So x is greater than 5 and x is greater than 3. Well, look, that's redundant. If it is greater than 5, it already is greater than 3, so really that just reverts back to greater than 5. And basically, that's like two separate questions from before on the numerator denominator of a fraction, and all that boils down to 3/5. Pause the video to have a closer look at that one. This one here, we just have a variable t, no big deal. T is greater than 4, well that would just be, in this case it's only the probability when x equals 5 is the only one we have there, and that's 0.15. Okay, between 1 and 5 exclusive, so that's 2, 3 and 4, and 0.3 plus 0.2 plus 0.1. I didn't write the notation down there just to save some time, and that's 0.6. So here's another conditional one at the end. Probability that t is less than 3 given that t is less than 4. So we put the probability of t is less than 3 and t is less than 4 over the probability that t is less than 4. Now look for redundancy. Okay, so if it's both less than 3 and less than 4, it makes this one redundant. So that's the same as the numerator is the same as the probability of t less than 3 over the probability that t is less than 4. And we get that from our table there. So, okay, just keep the length of the video down. If you go back to your table and work out probability when t is 2 and t is 1, you get 0.55, and t is 1, t is 2, and t is 3. Add them together, you get 0.75. It boils down to 11/15.